Hey everybody, welcome to your molecular geometry lecture. Depending on what page in the packet, depending on what packet you're in, whether you're in the honors packet or the CP packet, you guys might have different pages that this lecture appears on. So just go ahead and find the page where you see VSEPR theory. This is the theory or the understanding that is going to allow us to predict the shape that molecules make. Now, of course, we want to know the shape that they make, because between that and the difference in the electronegativity values of the atoms in the molecule, those two things together are going to help us determine the polarity of the molecule. Is this molecule polar or nonpolar? And that is going to determine that substance's properties. So we're on this long road to figuring out properties of covalent compounds. We have to understand how they bond and draw Lewis dot diagrams. Those Lewis dot diagrams are going to help us predict molecular geometry. Once we understand molecular geometry, then we'll talk about polarity, and then we'll talk about properties. So it's a lot to put together, but I think that's why chemistry is so cool, because you get this layering of knowledge and understanding to understand what's going on at the macroscopic level. Okay, so here we go. VSEPR theory stands for valence, shell, electron, pair, repulsion. Remember, the only electrons that are involved in bonding are your, obviously, valence shell electrons. And we know that because of like charges, electron pairs will repel one another. What does that mean about the shape of the molecule? A couple of things. First of all, just remind yourself that like charges repel. Molecules are going to form in three-dimensional shapes so that the electron groups are as far away from each other as possible in order to reduce those repulsions. So they're going to repel each other into these three-dimensional arrangements so that the electrons are as far away from each other as possible. There's one little tweak to that rule, and that is that lone pair electrons repel more strongly than bonded pairs of electrons do. Now, that's not going to make a whole lot of sense until we get into some of our drawings, but hang on to that idea. So these two ideas about reducing the number of repulsions or repelling as strongly as they can to get as far away from each other as possible, with lone pairs repelling more strongly than bonded pairs. All of this information is going to allow us to predict the shape that molecules make. Go ahead and pause the video here if you need a little more time to take those notes down. Here are just some of the shapes that we're going to find that our covalent compounds make. Now, if you are in CP chemistry, this is the extent of the shapes that you're going to learn. And if you're in honors chemistry, we are going to take it even further into 5 and 6 domain families. And what am I talking about domains and families? That you will find out here in a little bit. So that first shape that you see where all of the atoms are straight in a line across from one another, that shape is called linear. The next shape that you see where those three atoms, but they're no longer in a line, it looks like they've been bent downwards, has the name bent. The trigonal planar molecule is named as such because you can see that there are three atoms bonded to the center atom, so that's where you get that trigonal from. And planar, meaning they're all lying in the same plane. Tetrahedral, tetra meaning four, hedral meaning side. This is a four-sided molecule. There's sort of like three sides around the top and a side down on the bottom, like the little top of a diamond. That's a tetrahedral molecule. And the last shape being pyramidal, being like the little bottom of a pyramid. Now would be another good time to pause and sort of sketch those out as best you can. Now, I know in those ball and stick models, it might not be entirely clear how you should be drawing those. Don't worry, we are going to draw them together, but not until I show you a little demonstration. So we're going to go ahead and switch from our PowerPoint here to our webcam. Hello. Can you guys see me? I hope so. Oh, I forgot I have everything except my molecules. Let me pause this video and go get those. Okay, I'm back. I've got my molecules. So here are some of the molecules that you saw on that PowerPoint a minute ago. This is an example of a linear molecule. Now this linear molecule has double bonds on it. You don't need to be taking any notes right now. This is sort of an intro. So this has some double bonds, whoops, between the atoms, but you can see they are all 1, 2, 3 in a line. So this is a linear molecule. We also saw a bent molecule. Get my head out of the way. Ooh, there we go. Bent. This is like backwards for me. I need to find a way to flip my screen. There we go. All right. This is our trigonal planar. Do you see how all of these atoms are in the same plane? There's nothing sticking up or down. They're all lying flat in the same plane. Maybe it's easier to see it this way. They're all flat in the same plane. Trigonal planar. What else did I show you? I showed you tetrahedral. This is that three-sided one. It sort of looks like a little pyramid that's standing up here on my hand with one popping up out of the top. This is your tetrahedral molecule. And the pyramidal molecule as well, just the bottom of the pyramid. So we're going to come back to these three-dimensional molecules quite a bit as we bounce back and forth between our notes and my demonstrations. Okay, so now that you're familiar with the shapes that these molecules make, as well as the theory behind why they make these shapes, let's go ahead and take some notes. So flip to the next page in your packet, and you should see something that looks like this. All right, so we're going to do a couple of examples here. We're going to do 1, 2, 3, 5, 6. I think like 6 examples. 1, 2, 3, 4, 5. Yeah, I think we're going to do 6 examples on this page. So make sure you leave yourself enough room. All right, so for our first molecule that we are going to draw, let's draw the formula H. Whoa, that's an ugly H. All right, come on, Amanda. HCl. Let's draw our Lewis dot diagram for that. Remember, we're going to count up our total number of valence electrons. So 1 plus 7 makes 8. We're going to divide by 2, working with 4 pairs here. So my Lewis dot structure is going to look like this. H to my Cl, like so. Everybody here is satisfied, and my hydrogen is satisfied. Now, this is some new vocabulary for you. Electron domains and bonded versus non-bonded. Electron domains are simply areas around the central atom where bonded electrons or lone pairs exist. Now, these electron domains and whether they are bonded or not bonded is going to help us determine the geometry. Now, luckily, for this first simple example that we're doing, there is no central atom. And the definition says these are areas around the central atom. So because there's no central atom, we're going to say that this is not applicable and this is not applicable. Not for this example. We don't have to worry about it yet. And so all I have to think about is how would a hydrogen and a chlorine get as far away from each other as possible? Well, that would be in a line. The hydrogen and the chlorine. HCl. This molecule, when you just have 2 atoms in a line across from one another, is called 2-atom linear. And what would that molecule actually look like? Well, look like this. Oh my God, I'm not doing good this webcam situation. The white being my hydrogen and the green being my chlorine. You guys, I have serious issues with this being reversed. Okay, hydrogen, chlorine, straight across from one another. This is a 2-atom linear molecule. Okay, they're 180 degrees apart. Back to our smooth draw. Okay, let's add that bond angle in there, shall we? 180 degrees apart from one another. Okay, if you need to pause, now would be a good time, and we are going to do our next example. Not a bad straight line there. Okay, let's start working with molecules that have central atoms. Let's draw the Lewis dot diagram for CO2. Now these are all Lewis diagrams we've drawn before, so they should be pretty easy for you guys to come up with. So 4 plus 6 times 2, 16 divided by 2. We're working with 8 pairs of electrons. So my Lewis structure is going to be carbon connected to an oxygen, connected to an oxygen. I have 6 pairs left. Put them on my terminal atoms first. And I'm all out of electron pairs. There's my 8 pairs in total. And I can see my central carbon is not satisfied. So I'm going to take away some lone pairs and I'm going to make a double bond on both sides. If you're in honors chem, you learned using formal charge how to figure that out. And if you're in CP chem, you just took my word for it, that the double bond on both sides was the best option. Okay, now here's where we have to take into account these electron domain things, okay? So electron domains are areas around the central atom where bonded or lone electrons exist. So here's my central atom, here's carbon. How many areas around it have either bonds or lone pair electrons in it? And it doesn't matter that they are single bonds or double bonds or triple bonds, it's just how many areas. And I can see that there are 2 areas. Like there's an area here with bonds in it, and there's an area there with bonds in it. Okay, so we would say that this molecule has 2 electron domains, and both of them are bonded. Okay, so they have 2 bonded domains. Now, you might be asking, who cares and why, right? Like, what does it mean to have a central atom and to have 2 bonded domains? Well, I have a demo that I would like to show you guys to help you understand. So here we go. I want you to imagine these 2 balloons, okay, as electron domains, as areas around the central atom where electrons can exist. So the central atom is going to be represented by me tying these 2 balloons together in the middle. So like the knot in the middle of the balloons. You didn't know I was a circus performer, did you? The knot in the middle, there we go. The knot in the middle is representing my central atom, okay? So if that's the central atom, do you guys see how these balloons or these 2 bonded domains have repelled each other 180 degrees away from each other in a line? They were not like squished together up like this, like a 90-degree angle. Why? Because they repel one another. They take up space. So these domains around the central atom will arrange themselves to be as far away from each other as possible. That's what VSEPR theory tells us. So here's my central atom. Here are the electrons, the bonds taking up space. And out here is where the oxygens would bond to, like so. Can I get these to line up? Are you guys tired of me trying to without having practiced this? Aha, there we go. So those big orange balloons are representing those bonded areas around the central atom that are resulting in the oxygens being pushed out 180 degrees to the sides of that central carbon. And so what we end up with, again, is a linear arrangement of our molecule. Okay. Hopefully that makes sense. It's much better to do this lecture in the classroom where I am three-dimensional and so are their balloons, as opposed to this like flat video screen. Back to our drawings. Here we go. Okay, so we now have a 3-atom linear. Do I have the right color here? Let's see. So here's my oxygen on one side. I'm going to show my double bonds as little curved bonds. Here's my carbon in the middle. Here are my double bonds on the other side. And there's my other oxygen over there. These bonded pairs repelled one another to 180 degrees apart, just like they did in the 2-atom linear, except this time we're going to call this 3-atom linear. Oh, there's an A in linear. Again, now would be a good time to pause before we move on to our next example. Okay, let's do, what do I want to do next? I want to do BH3. Okay, boron has 3 valence electrons. Hydrogen has 1 times 3, 6. Divided by 2, 3 pairs. Okay, boron is going to go in the middle. 3 pairs to work with. 1, 2, 3. And I'm all out of pairs. Now here's where you would normally look to see if you could make double or triple bonds, but in this case you can't. This molecule still forms though, you guys. It's called a suboctet. So take my word for it that this is in fact a thing. All right, let's look at our central atom. How many domains or areas around that central atom are there? Well, there's a bond here, so that's 1 area. This is 2 areas. This is 3 areas. So we have 3 domains. And all 3 happen to be bonded. Just like in the CO2 example, there's no lone pairs on there. And so now you're probably wondering, well, like, how are these guys going to arrange themselves? Well, lucky for you, I have another balloon. So I'm going to take my 2 domains that were tied together, and I'm going to add to it a 3rd domain, where I'm going to tie a 3rd pair of electrons onto that central atom. And we're going to see what happens to the shape. Okay. Voila. Do you see how now they've all gotten smushed a little bit, right? Because we have another one taking up some space. But they're all lying in the same plane. They're flat up against my board. Or you could think about them flat like so. They're all lying in the same plane. This is that trigonal planar geometry that we were talking about. And if you have 3 atoms all lying in the same plane, they will be 120 degrees apart from one another, right? 360 divided by 3 is 120. This is trigonal planar. I keep trying to line these things up. There we go. Oh. Voila. Okay? Trigonal planar geometry. So when we originally drew our Lewis dot structure, we drew it looking like they were 90 degrees apart from one another. Let's go back to that. this Lewis structure that I drew makes it appear that these guys are 90 degrees away. In fact, the more you get used to this, the more you get used to drawing your Lewis structures to sort of better represent what the geometry is actually going to be. So I might, in fact, draw my Lewis structure instead, like so, to start showing my shape even when I'm drawing my Lewis structure. You don't have to do that, but you might find yourself doing it as you get more familiar. So now let's draw our ball and stick model. Here's my boron. I've got a hydrogen up here, right? They can get farther than 90 degrees away from each other. They can get 120 degrees away from each other. Okay, so my bond angle here, you know what? I'm gonna do it on the other side. The bond angle is the same on all sides, angles between the bonds. But I just wanted to give myself some more room to write the name. The name of this molecule is trigonal planar. Okay. And in fact, maybe what I'll do here, while you guys write that out, is I'll squish this Lewis dot structure up a little bit more. All right, let's do another example. Now, I'm not going to draw a full purple line between these guys because this next example that I'm about to draw is in this, what we call 3-domain family. Okay, so it is also going to have 3 areas around the central atom, but there's going to be a slight change. So, next example, NO2, 1-, our polyatomic ion nitrite. 5 plus 6 times 2 plus 1 for that 1- charge. So 12, 13, 18. Working with 9 pairs of electrons here. All right. So I'm going to go nitrogen in the middle, oxygen, oxygen. I have 7 pairs left. 1, 2, 3, 4. Nope, sorry. 1, 2, 3, 4, 5, 6, 7. Remember, if you have any pairs remaining, you can go on to the central atom. I'm all out of pairs. Check to see if everybody's satisfied. I'm going to need a double bond somewhere. This is one of those situations where you could have done the double bond on the right or on the left. Either one is acceptable. Oops, that looks ugly. So if you're in CP, put the double bond either on the right or on the left. If you're in honors, you know that this means that there is resonance and that this double bond is actually spending equal amounts of time here and here, and you would have a 1.5 bond bond order. So be thinking about resonance and how that bond is spread out over multiple locations and how you would need to draw that. All right, so I'm going to put brackets in charge because it's a polyatomic ion. So there's my Lewis structure. Now let's look at electron domains. How many areas around the nucleus have things in them? Well, there's an area here, it's got a single bond in it. There's an area here, it's got a double bond in it. And there's an area here that's got a lone pair in it. So I'm still in this 3-domain family. I still have 3 domains. But this time, you guys, I have 2 bonded and 1 non-bonded or lone pair. And remember what we said when we were talking about VSEPR theory is that lone pairs take up more space than bonded pairs do. They repel more strongly. So if I'm like looking at this Lewis diagram here that I just drew, maybe it would be helpful to think about that domain. Oops, pen. So here's this domain. There's those electrons. You know, it would be helpful to think about this as taking up more space than these bonded domains do. Or if you would rather see what I'm talking about on the actual balloons, imagine, if you will, that one of these balloons has a lone pair in it. As opposed to just being all the same size bonded domains, one of these balloons has lone pair electrons in it. And what does that mean? That means that this balloon would get blown up bigger. If this balloon on top blew up bigger, you guys, these two balloons down here on the bottom, this is not the best, there we go, would get smushed downwards because the balloon on the top would be taking up more space than it was before. Okay, so if this balloon gets blown up bigger because of a lone pair, these two domains get pushed closer together. And that 120-degree bond angle that once existed in our trigonal planar geometry is now a little less than 120 degrees. It got smushed by that big lone pair repulsion. Let's draw that out as a molecular geometry. Okay. Oh, I forgot to show you the molecule. I'll do it after. Some consistency would be nice from your teacher, you know. All right, let's draw it. Okay, so my central atom is nitrogen. And we've got a single bond on this side to an oxygen and a double bond on this side to an oxygen. And up here is a lone pair. Now, if you want to draw that lone pair in, you can absolutely do that, or you can just leave it blank. So you'll see both things happen. You'll see geometries with no lone pairs on them. They're just omitted, or you'll see them drawn in. So let's just draw in that lone pair. Taking up a lot of space up on the top of my molecule. And so that lone pair takes this bond angle that before was 120 degrees and makes it a little less than 120 degrees. Depending on what the molecule is, it might be like 117, it might be 114, just depends on what atoms are involved in the bond. And we're going to name this molecule bent, because these atoms are not in a straight line. They have been bent down. They've been pushed downwards by this lone pair. You know, honestly, I don't even like how I drew that lone pair. It's like all off to the left. See if I can get them to be straighter. Am I driving you crazy? I'm sorry. That's a little better. Ugh, and my green circle. There we go. All right. Oh, I need to show you this molecule, right? What am I trying to show you? I'm trying to show you bent. Here it is, right? So you can imagine that this is your nitrogen here in the middle. This is actually representing an oxygen atom. Oops, doesn't matter. So this is a nitrogen, imagine this is a nitrogen atom, and you've got some oxygens on the side. You'd have this bent shape. Hey, you know what, fine. I'll show you an actual nitrogen molecule. It's a blue one. Ooh, and this one has a lone pair on the top. So this is a better way to sort of imagine the bent molecule, because you can actually see this lone pair on the top taking up the space and your oxygen atoms being down here at the bottom. Technically, if these were oxygens, these would be red. I'm really being a not great teacher. La 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 la. Just getting some red oxygen molecules. You guys don't even know the colors of the molecules, so you probably don't even care. I care. See my OCD really coming through in the making of these videos. Aha! There we go. There is your bent NO2 molecule. Ugh. Okay. We're going to go on to a 4-domain family now. So we have 2 more examples that we need to do. in the 4-domain family. Do you think I can tie a 4th balloon? I believe I can. Here we go. Now I am going to draw that nice purple line between these guys because we're going to add a 4th domain. So and scroll. Let's draw. What heck color was I using? Was I using green or was I using purple? I was using green. Okay. Let's draw the structure for CH4. So 4 carbons, 1 times 4, 8, divided by 2, 4 pairs. All right, so we're going to put carbon in the middle. We're going to connect it to our 4 hydrogens. Oops, sorry, you guys, getting a little squishy. All right, I'll move. Carbon, 4 hydrogens. Used up all of my pairs of electrons, and everybody's satisfied. If I look at my areas around the central atom, I have 1, 2, 3, 4 domains. So this is now the 4-domain family. And in this particular example, all 4 domains are bonded. You guys, I lied. We're doing 3 more examples. Hope you have room. All right, 4 bonded. So are you ready to see me tie a 4th balloon onto our structure? Oh, my 4th balloon rolled away. Aha. Here we go. Putting a 4th domain onto my central atom. What is going to happen to the shape? Now, when I drew my Lewis diagram, it looked like they were 90 degrees apart from one another. But in reality, they are not 90 degrees apart from one another. In fact, what you have is these balloons are now popping into different planes. They're not all in the same plane. You've basically got 3 of them at the bottom and 1 of them poking out the top. This is the tetrahedral geometry. If I wanted these all 90 degrees away from each other, I'd have to smush this balloon. I'd have to smush it in there for them to all be flat and in the same plane. Oop, ignore that lone pair there. There we go. There's no lone pairs yet. All bonded domains. So this, if they were all 90 degrees away from each other, you'd have a lot more repulsions or stronger repulsions happening. The way it would prefer to arrange itself when I first just tied these balloons together is popped out like that into this space where you've got 1 balloon sitting on the top and 3 on the bottom. This is a tetrahedral geometry. What does that look like in a ball and stick model? Because remember, these are the areas around the central atom. Here is my black central atom with my 4 molecules on the ends. Oh, those were supposed to be hydrogens, and these green ones are chlorines. Don't worry, I won't change it. The shape would be the same. Okay? All right, so there's my go-away balloons. Here's my tetrahedral geometry. Let's draw it. Okay. So my 4 bonded domains. Now trying to draw, these things three-dimensionally on a 2-dimensional screen is like not the easiest thing in the world to do. So this is how I do it. I draw my central atom first, my carbon, and then I try to draw some perspective, like those hydrogens on the bottom, sort of the ones on the bottom of your pyramid. Hydrogen, hydrogen. Ugh, nope, I'm not satisfied with this drawing. I need to make it bigger. That's the problem. All right, we're gonna take a little more space with this one, you guys. Carbon. Here are my 3 hydrogens that were down below my carbon. And here's my 1 hydrogen. Oh my gosh, off center. Here's my 1 hydrogen sticking out the top. Good grief. How many times am I going to draw this? There we go. This arrangement, and I know it's tough to draw, sometimes you're actually going to see in some of the fancier textbooks, to show the atoms that are going like back into the screen, they'll draw with like dashed lines like that, and the ones popping up at you with, you know, fully shaped or fully drawn in triangles like that. So sometimes you'll see stuff like that. We're not gonna bother, but when you go on to take organic chemistry and the 3-dimensional shapes really matter, you'll have to draw some really crazy 3D stuff. This is good enough for now. Try to make it look tetrahedral. Now, in the 2-dimensional diagram, the bonds don't look like they are all the same bond angle, but they are. Okay, the bond angle here for all of these bonds is 109.5 degrees. And it's symmetrical all the way around. And the name of this shape is tetrahedral. All right, let's stick with this family. So we're going to stick with 4 domains, and now we're going to do our second to last example, NH3. 5 valence electrons, 1 times 3, 8 divided by 2, 4 pairs. Okay, so we've got our nitrogen to our 3 hydrogens. That 1 pair that remains cannot go on hydrogen, so it has to go on that central atom. So if we're looking up for domains, we've got 1, 2, 3 bonded domains. And remember, that lone pair is going to take up a little more space. So we're still in this 4-domain family. But this time, 3 of them are bonded. And 1 of them is lone. So imagine in this tetrahedral arrangement that I had up here before, if that wasn't a bonded hydrogen, if in fact that was a lone pair taking up more space, what's going to happen to this bond angle for these hydrogens down at the bottom? Be thinking about that as I pull up our molecule. My hydrogen up at the top is no longer a hydrogen, now it's a lone pair. If that balloon up at the top gets blown up bigger and takes up more space, it's going to smush these other balloons down more. And that 1095 bond angle is going to get smushed and a little less than 109.5 degrees. And this is the shape, once that bond angle gets smushed and there's no longer an atom up here at the top, but a lone pair. Oh geez, I took apart the molecule that I needed to show you guys this. Let's make sounds like we're in the circus. Ugh. Okay, voila. This right here is my trigonal pyramidal molecule. So I have those 3 bonded atoms down at the bottom, but instead of a bond up here at the top, I have a lone pair that's taking up more space than a bonded pair would. So you can see it's very similar in geometry to my tetrahedral. The bottom parts of these molecules are the same. Flip that over. I need to mirror my image so I don't struggle so much. Okay, so these are the same similar shape, but instead of this bonded pair up here, we have a lone pair, and that lone pair takes up more space. So the 1095 bond angle that was going on down here at the bottom is now smushed down a little bit, a little less than 109.5. Let's draw it. Okay. So I'm going to draw my central nitrogen. I'm going to smush my hydrogens down here a little bit. into a little tighter pyramid than they were before. And my bond angle is now a little less than 109.5 degrees versus this bond angle, both up here, remember it's symmetrical, and down here, 109.5 degrees. It's going to be less than in this molecule. And that's because that lone pair is taking up more space than the bonded pairs do. I don't know why I can't end these little teardrop shapes in the manner in which I want to. That's ugly. Hopefully you guys are still writing. And this just buys you some more time while your teacher fusses with her geometry. There, good enough. There's my lone pair taking up more space. All right, name for this shape is trigonal, because there's 3 atoms bonded, pyramidal, because you've got a pyramid down there on the bottom. Trigonal, pyramidal. Oh shoot, I went too far, and now you guys can't see my drawings. I'm very sorry about that. There we go. Now can you see them? Oh no, still no. I went past my point where I wasn't supposed to go. All right, give it a pause there if you need to. Tetrahedral and trigonal, pyramidal. We need to do one more example, still in this 4-domain family. Okay, so let's go back to our molecule. All right, so we had 1 lone pair. Oh, I didn't do an example yet. Well, let's preview it. Let's imagine I have 2 lone pairs. It's going to be our last example. I'm jumping all over the place in terms of the order in which I'm showing you guys these things. Okay, 2 lone pairs now. So imagine that these 2 balloons here on the top are taking up even more space. What's going to happen to this bond angle that was less than 109.5? It's going to get smushed even more down because of those lone pairs up on the top that are taking up so much space up there. Okay, so this bond angle is going to get smushed down even more, and it's going to be bent. Those guys up there, those are my lone pairs. All right, what does this look like in terms of an actual molecule? Kind of looks like a Mickey Mouse. So these are my lone pairs up at the top, and now remember, we had 4 things bonded originally, right? We were in this tetrahedral family with 4 things bonded. We went to 1 lone pair, and it was pyramidal. Went to 2 lone pairs, and now all of a sudden we're just left with a bent shape again. This is bent just like we had before, but the angles are going to be different. So let's take it back to our drawings, and you'll see how those 2 things differ from one another. Okay, so I need to go back to... Oh my gosh, I just drew a random green line. Here we go. All right, our last example is water. H2O. 1 times 2 plus 6 is 8, which means I've got 4 pairs to work with. Hydrogen can never go central, so we're going to connect our oxygen to our hydrogen, to our hydrogen, lone pair, lone pair. Now, I know this looks like everybody is 90 degrees apart from one another, but remember, we're working in 3-dimensional space, okay? So let's count up our domains. 1, 2, big domain 3, big domain 4. Okay, so these are all taking up space in this 4-domain family. This time we have 2 bonded and 2 lone. So imagine here this less than 1095 degree bond angle. If one of these got replaced with another lone pair, it's going to get smushed even more. So here's my oxygen. One of my hydrogens is going to be smushed down here, and one of my hydrogens is going to be smushed down there. This bond angle is going to be less than 109.5 degrees. And we're going to call this shape bent. Just like, oh geez, did I go too far again? Just like we had a bent previously, but I'll show you the difference here in a second once I draw these lone pairs in. Like Mickey Mouse ears of lone pair electrons. This bent shape differs from our bent shape that we had up here. This bent shape has a 120 degree bond angle because there's only 3 things around the central atom. And so 3 things take up less room than 4 things. Okay, so when you're in this 3-domain family with a lone pair on the central atom, it's 120 degree bent. When you are in the 4-domain family, there's 4 things around that central atom. And with 4 things around the central atom, you're going to be at less than 109.5 degrees. So these are 2 different types of bent molecules. This being a 4-domain bent molecule, and this being a 3-domain bent molecule. So they kind of look the same, but this one down here is going to have a smaller bond angle. Okay, that is it for now if you are in CP. If you are in honors, we are going to do a subsequent lecture where we go to 5 and 6 domains. So stay tuned for that, and great job today.